You're watching this video right now. Your eyes are processing light bouncing off a screen. Your brain is decoding symbols and converting them into meaning, and you're absorbing information. Simple, right? Just a straightforward transfer of data from the external world into your consciousness. Here's what you believe, what you've believed your entire life. The world exists out there, solid, real, independent. A tree falls in a forest, and whether or not you're there to witness it, the tree falls. The moon sits in the sky, whether you look up or keep your eyes glued to your phone. Your coffee cup rests on your desk, whether you're staring at it or not. Reality, you've been told since childhood, doesn't need you. You're just a passenger, a consciousness riding along in a meat suit, observing a universe that was here 13.8 billion years before you were born and will continue for trillions of years after you're gone. You are, in the grand scheme of things, irrelevant to the mechanics of reality itself. This is the lie. Not a metaphorical lie, not a philosophical debate about the nature of perception, not some New Age mysticism about consciousness creating reality. I'm talking about a physics lie, one that's been confirmed by thousands of rigorous experiments, proven by equations that govern the subatomic realm, verified in laboratories across the world, and one that completely dissolves the moment you understand what's actually happening when you observe something. Because here's the truth that'll make you question everything you think you know. Until you look, the universe doesn't choose. The electron doesn't decide where it is. The photon doesn't pick a path. The quantum world exists in a ghost state of pure possibility, a shimmering fog of maybe here, maybe there, maybe nowhere and everywhere simultaneously. And your measurement, your observation, is what forces reality to crystallize into something definite. You don't just see the world, you collapse it into existence. Think about the screen you're staring at right now. You assume the pixels were glowing in their precise arrangement before you looked. You assume the atoms making up your desk were positioned exactly where they are, whether or not you checked. You assume your room exists in a definite state, even when you close your eyes. But quantum mechanics, the most successful scientific theory ever devised, tested to absurd precision, says otherwise. At the smallest scales, at the foundation of everything you see and touch, particles don't exist in definite states. They exist in superposition, simultaneously in multiple states, multiple places, multiple versions of reality layered on top of each other, like a shuffled deck of infinite cards spread across a table. Only when something observes them, measures them, interacts with them in a very specific way does the deck get dealt. One card becomes real, one position becomes actual, one version of reality crystallizes while the others vanish as if they never existed. And here's the part that should make your skin crawl, the part that physicists have been arguing about for a century. We don't know where those other possibilities go. We don't know why observation has this reality-creating power, and we definitely, absolutely don't know what counts as an observer. Is it consciousness? Does it require a mind, awareness, subjective experience? Is it any measuring device, even an unconscious machine? Is it just any interaction between particles? Is it the universe observing itself through us, through everything? Or is there something even stranger going on? Are we creating the past by observing it now, reaching backward through time to solidify history? The questions get weirder the deeper you go. Welcome to the observer paradox, where the line between you and the universe isn't just blurred, it fundamentally doesn't exist at all. Where the observer and the observed are two sides of the same coin, where reality is less like a movie you're watching and more like a dance you're performing, whether you realize it or not. Richard Feynman had a superpower. While other physicists were drowning in mathematical abstraction, writing equations that sprawled across chalkboards in incomprehensible strings of Greek letters and operators, Feynman would draw little pictures, simple diagrams, stick figures almost. When physicists argued about wave-particle duality using terminology that required a PhD to parse, Feynman would lean back and say something like, "Imagine you're a photon at a party, and someone asks you, 'Are you a wave or a particle?' And you'd look at them confused and say, 'Depends who's asking and how they're measuring me.'" Feynman won a Nobel Prize for his work on quantum electrodynamics, but his real genius wasn't the math, it was the clarity. He had this almost pathological hatred for mystery's sake, of people making things sound complicated to seem smart. He believed deeply that if you couldn't explain something to a reasonably bright child, you didn't really understand it yourself. You were just regurgitating formulas without grasping the physical reality beneath them. So, when it came to the observer paradox, this bizarre, almost mystical-sounding notion that reality seems to need an observer to become definite, Feynman stripped it down to absolute first principles. Start here, he'd say. What is observation? Not philosophically, physically. What does it mean to observe something? You think observation means looking. You picture yourself standing back, passively receiving information from the world, like a camera recording a scene. But in physics, at the quantum level, observation means something completely different. It means interaction. It means one thing affecting another thing. To see an electron, you have to bounce a photon off it. To measure its position, you have to touch it with something, a detector, a field, some other particle, some physical system that interacts with it and extracts information. And here's the kicker that Feynman emphasized over and over. You cannot touch something without changing it. That sounds innocent enough at first. Sure, measuring disturbs things a little, like taking someone's temperature. The thermometer absorbs a tiny bit of heat, slightly cooling what you're measuring. No big deal. But Feynman realized it wasn't about disturbance in the classical sense. It wasn't about accidentally bumping things around. It was about something far profound, information. Before you measure an electron's position, it isn't just somewhere you don't know about. It's not hiding in some definite location, waiting for you to discover it like a coin under a cup in a shell game. It's in superposition, a genuinely quantum state where it exists in all possible locations at once. Not probably here, probably there, but actually, physically smeared across space in a cloud of probability, like a blurred photograph where every version of reality is layered on top of each other until the moment of measurement. The moment you measure it, you're not discovering where it was, you're forcing it to pick. You're compelling the universe to choose one reality from the infinite possibilities and make that the only reality. Think about that for a moment. Really let it sink in. The electron wasn't sitting at position X, patiently waiting for you to find it like an Easter egg hidden in grass. It was genuinely, physically distributed across multiple positions simultaneously. Your measurement is the thing that makes it real in one specific place. Before that moment, where is the electron wasn't a question with a hidden answer. It was a question without an answer at all. Feynman's genius was turning this into stories and thought experiments that made the physics visceral. He'd say, imagine the universe is a novelist who absolutely refuses to commit to a plot. Every possible storyline exists simultaneously in the manuscript. The detective finds the killer in the library, the detective finds the killer in the garden, the detective never finds the killer, the detective is the killer, there is no killer, everyone is the killer. The story exists in all these states at once, superimposed in a kind of narrative quantum fog, until you, the reader, open the book and start reading. The act of reading forces the novelist's hand. Suddenly, one storyline crystallizes into what happened. The others evaporate like morning fog in sunlight, leaving no trace they ever existed. You didn't just read the story, you collapsed it into existence by choosing to observe it. And here's Feynman's famous punchline, the quote every quantum physics student learns. If you think you understand quantum mechanics, you don't understand quantum mechanics. He meant it literally, because the moment you truly accept what quantum mechanics is telling us, you realize that everything you thought you knew about reality is wrong. Reality is participatory. The universe isn't a stage you walk across as a spectator, passively observing a play that would happen the same way whether you were there or not. It's a dance, and you're not watching from the audience, you're the partner. Every step you take, the universe responds. Every observation you make, reality shifts. You and the universe are creating each other, moment by moment, in an intimate feedback loop that's been going on since the Big Bang and will continue until the heat death of everything. Feynman understood this, and it haunted him, because it meant that at the deepest level, we don't just live in the universe, we are part of its fundamental operating system. All right, let's crack open the machinery. Let's get into the actual physics. How does this observer effect actually work? What's happening beneath the surface of reality? There's one experiment that reveals the observer paradox more starkly than any other. It's been called the most beautiful experiment in physics. Feynman himself said it contains the only mystery of quantum mechanics. Everything else is just commentary on this. It's called the double-slit experiment. Here's the setup. Imagine you have a barrier, a wall, with two narrow slits cut into it, positioned vertically and parallel to each other. Behind the barrier, at some distance, you place a detector screen that lights up wherever particles hit it. Now you fire electrons toward the barrier, not a spray of them, one at a time, individual electrons, like shooting marbles one by one toward the wall. Common sense says this: each electron is a tiny particle, a little ball of matter. It travels through space, encounters the barrier, and goes through either slit A or slit B, one or the other, not both because it's a particle, and particles don't split in half. Then it continues in a straight line and hits the detector screen, leaving a dot of light where it impacts. Fire enough electrons, one by one, and you should see two vertical clusters of dots forming on the screen. One cluster behind slit A, one cluster behind slit B. Simple geometry. This is what happens when you shoot actual marbles through two openings. But that's not what happens. What you get instead is an interference pattern, a series of alternating bright and dark vertical bands rippling across the screen, like the striped pattern you see when two sets of water waves overlap in a pond. Dark bands where waves destructively interfere and cancel out. Bright bands where waves constructively interfere and reinforce each other. This is the unmistakable signature of a wave. Somehow, impossibly, each individual electron is going through both slits at the same time. It's interfering with itself. One version of the electron passing through slit A creates a wave. Another version simultaneously passing through slit B creates another wave. And these two waves overlap and interfere on the other side, creating the pattern of bands. Each single electron, fired one at a time with seconds between shots, is acting like it explored every possible path simultaneously and interfered with alternate versions of itself. Particles aren't supposed to do that. Waves do that. Water waves, sound waves, light waves. They spread out, they go through multiple openings at once, they interfere with each other. But electrons are matter. They have mass. They're particles. Except, apparently, they're not when you're not watching. Now here's where reality starts to unravel completely. Place a detector at each slit, tiny sensors that simply register which slit each electron passes through. You're not blocking anything. You're not zapping the electrons with energy. You're just watching, just observing which path each electron actually takes. Run the experiment again. The interference pattern disappears, completely, vanishes. The instant you observe which slit the electron goes through, it stops acting like a wave smeared across both paths. It becomes a definite particle, taking a definite path. You get exactly what common sense predicted from the beginning. Two boring clusters of dots on the screen, one behind each slit with no interference pattern whatsoever. By observing, you fundamentally changed what the electron was. Not you disturbed it, not you accidentally bumped it, you changed its essential nature. When unobserved, it behaves like a wave, spreading through space, going through both slits, interfering with itself. When observed, it behaves like a particle, taking one definite path, existing in one definite location. This isn't measurement error. This isn't clumsy equipment jostling things around. This has been repeated thousands of times with increasingly sophisticated technology. We've done it with photons, electrons, atoms, even large molecules containing thousands of atoms. The result is always the same. The universe is telling you something profound and deeply unsettling. The electron doesn't have a definite path until you measure it. It genuinely exists in superposition, in all possible paths, simultaneously, and your observation is what forces it to pick one and only one. The act of observation doesn't reveal reality, it creates it. Now let's meet the mathematical character at the heart of this story. In quantum mechanics, every particle, every electron, photon, atom, everything, is described by something called a wave function, usually written as the Greek letter psi. Think of the wave function as a map of possibility. It doesn't tell you where the particle is, it tells you where it might be if you were to measure it. Imagine a fog rolling across a landscape. The fog is thickest in certain areas, thinner in others, and completely absent in some places. The wave function is that fog, mathematically speaking. Where the wave function is large and dense, the particle is more likely to appear when measured. Where it's thin or small, less likely. Where it's zero, impossible. But here's the absolutely crucial part, the thing that separates quantum mechanics from just classical physics with uncertainty. Until you measure, the particle isn't in the fog somewhere, you just don't know where. The particle is the fog. It's genuinely smeared across every location where the wave function isn't zero, existing in all those places simultaneously in superposition. It's not that you lack information about where it is, it's that where it is a meaningless question before measurement. The particle doesn't have a definite position. It has only a probability distribution of possible positions, all equally real in a quantum sense. The equation that describes how this possibility evolves over time is called the Schrödinger equation. It looks like this. I h bar d psi dt equals h hat psi. I know, it looks like alien script, but stick with me. Let's translate this into something human. Think of this equation as describing how possibility flows through time, like water flowing through a landscape. The psi, the cloud of maybe, all the potential futures, all the possible configurations, layered together in superposition. The h hat, called the Hamiltonian, but think of it as the environment, represents all the forces, fields, and physical rules acting on the particle. The rest, the I h bar and d dt, are just mathematical machinery describing how things change in time. The equation says, given the current state of possibility, the wave function, and the rules of the game, the Hamiltonian, here's exactly how that cloud of possibility will evolve, spread, flow, and transform as time passes. And here's the beautiful part. The wave function evolves smoothly, predictably, deterministically. It flows like a river, spreads like ripples, splits and interferes with itself, creating those interference patterns in the double-slit experiment. There's no randomness in this evolution. Given a starting wave function, the Schrödinger equation tells you exactly what it will look like at any future time. It's perfectly deterministic. Until you measure. Then something shocking happens, something the Schrödinger equation doesn't predict, doesn't describe, and can't explain. The wave function collapses. All those smoothly evolving possibilities that were smeared across space suddenly contract to a single point. The fog condenses into a droplet. The particle appears here and not there. One outcome becomes real. The others vanish instantly, as if they never existed at all. This is called wave function collapse, and it's the single most mysterious, controversial, and poorly understood aspect of quantum mechanics. Because nothing in the Schrödinger equation, the equation that successfully describes how quantum systems evolve, says this should happen. The equation describes smooth, continuous evolution of the wave function, not sudden, discontinuous collapse. Collapse is something extra, something we have to add to the theory by hand. And nearly a century of debate, nobody knows why it happens, how it happens, or even if it really happens the way we think it does. We just know experimentally that something like collapse occurs, and that observation seems to trigger it. Let's dig even deeper into what it means for something to be in superposition, because this is where most people's intuition completely breaks down. Imagine you flip a coin. While it's in the air, spinning, you don't know if it'll land heads or tails. But here's the crucial thing. The coin is actually heads or tails at every moment during its flight. You just don't know which because you haven't looked yet. Your ignorance doesn't change the coin's reality. There's a fact of the matter, hidden from you temporarily, but real nonetheless. Quantum superposition is nothing like that. An electron in superposition isn't heads or tails, we just don't know which. It's not hiding a secret definite answer waiting to be revealed. It's heads and tails simultaneously, both at once, genuinely, physically, with no hidden reality underneath. The electron exists in a state that has no classical equivalent whatsoever, a state where contradictory properties coexist in a kind of quantum limbo until observation forces reality to choose one and eliminate the others. Let me give you a better analogy. Imagine you're a character in a video game, but the game is running on a hypothetical quantum computer. As you walk down a hallway toward a door, the game engine doesn't preload whether the door will be on the left wall or the right wall. Instead, it holds both possibilities in memory simultaneously, door on left and door on right, as a literal superposition in the quantum circuits. Only when you get close enough that the game needs to render the door on your screen does the quantum processor collapse that superposition and commit to one option or the other. Before you looked, both doors existed in the code, equally real in the computational substrate. After you looked, only one door exists in your rendered experience, and the game has erased all evidence of the other possibility. The universe, according to quantum mechanics, works exactly like that quantum video game. Reality is the code running in superposition, and observation is what renders it into definite classical experience. But here's what makes it even stranger. You can prove mathematically and experimentally that the electron isn't just in one state that you're ignorant about. Physicists have performed experiments called Bell test experiments that definitively rule out the possibility that particles have hidden definite properties before measurement. The Nobel Prize in Physics in 2022 was awarded exactly for this, proving that quantum mechanics really is as weird as it seems, that particles genuinely don't have definite properties until measured, that reality at the quantum level is fundamentally probabilistic and undefined until observation forces it to crystallize. There's no hidden clockwork underneath. The fuzziness is real. Now let's make things even weirder by introducing quantum entanglement, what Einstein famously called spooky action at a distance, and what's intimately connected to the observer paradox. Imagine you create two particles in such a way that their properties are correlated, their wave functions are linked. Maybe you create them from the same source, so their spins must be opposite, or their polarizations must be perpendicular. These particles are now entangled. Here's the strange part. You can separate these particles by light years, sending one to Earth and one to Alpha Centauri, and they remain connected in a quantum sense. Neither particle has a definite spin until measured. Both exist in superposition. But the instant you measure one particle and its wave function collapses to, say, spin up, the other particle's wave function instantaneously collapses to spin down, no matter how far apart they are. It's as if measuring one particle sends a signal to the other faster than light, telling it what state to be in. Einstein hated this. It seemed to violate relativity, which says nothing can travel faster than light. He thought it meant quantum mechanics must be incomplete. There must be hidden variables determining the particle's states in advance. But experiments have proven Einstein wrong. The correlation is real, instantaneous, and genuinely spooky. Measuring one particle doesn't send a signal to the other in any classical sense. Instead, the two particles share a single wave function that describes them both as a unified quantum system. When you measure one, you collapse the entire wave function, which determines the state of both particles simultaneously. Entanglement reveals something profound. Particles aren't really separate objects that happen to be correlated. They're aspects of a single quantum system, fundamentally interconnected in a way that has no classical parallel. And here's where it connects to the observer paradox. Your observation doesn't just affect the particle you're measuring. It can instantaneously affect another particle light years away, because both particles are part of the same quantum reality that your observation is collapsing. You're not just observing, you're editing the universal wave function that describes everything. Now let's shatter what's left of your common sense completely. You're holding a coffee cup right now, or maybe you're sitting in a chair. Whatever, pick an object near you. It's solid, definite, unquestionably there. If you close your eyes, you know with absolute certainty it doesn't disappear. If you look away, it doesn't suddenly quantum tunnel to the other side of the room. But that coffee cup is made of atoms, roughly 10 to the 24 of them, a trillion atoms, each containing electrons and protons and neutrons, and those particles are made of even smaller things like quarks. Every single one of those fundamental particles follows the rules of quantum mechanics. Every electron in your coffee cup exists in superposition until observed. So here's the question that physicist Erwin Schrödinger asked in 1935, and which physicists still argue about today. If individual particles exist in superposition until observed, what about objects made of trillions upon trillions of particles? What about your coffee cup? What about cats? What about people? Schrödinger illustrated this problem with his now famous thought experiment. You've probably heard of it, Schrödinger's cat. Here's the setup. You take a cat and put it in a sealed box. Inside the box, you place a diabolical quantum device, a vial of poison gas connected to a detector aimed at a single radioactive atom. Radioactive decay is a quantum process. The atom has, say, a 50% chance of decaying within 1 hour. If it decays, the detector notices, triggers a mechanism that shatters the vial and releases the poison, killing the cat. If the atom doesn't decay, the cat lives. Now you close the box and wait 1 hour. According to quantum mechanics, the radioactive atom exists in superposition, decayed and not decayed simultaneously, until something observes it and collapses its wave function. The detector is part of the quantum system, so it's also in superposition, triggered and not triggered. The vial is in superposition, broken and intact. The poison is in superposition, released and contained. And therefore the cat is in superposition, alive and dead at the same time. The cat exists in a quantum fog where it's simultaneously a live, breathing animal and a corpse until you open the box and observe it, forcing reality to choose one outcome. Schrödinger proposed this thought experiment not to celebrate quantum mechanics, but to show how absurd it becomes when applied to everyday objects. A cat can't be simultaneously alive and dead. That's ridiculous. That violates everything we know about macroscopic reality. And yet, if particles obey quantum rules and cats are made entirely of particles, where exactly is the boundary? At what scale does superposition break down? How many particles can you have in superposition before it becomes too big and collapses? We still don't have a definitive answer. Several interpretations of quantum mechanics try to solve this problem. The Copenhagen interpretation, the traditional view, says that large objects can't maintain superposition because they interact with too many other particles in their environment. All those air molecules bouncing off the cat, all the photons hitting it, all the thermal vibrations, these constitute constant measurements that collapse the wave function almost instantaneously. This is called decoherence. The cat is never in superposition long enough for you to notice because the environment is constantly observing it. But that raises a question. What counts as an observation by the environment? Is it any interaction? And if so, doesn't that mean everything is constantly being observed and collapsed, leaving no room for superposition at all? The many worlds interpretation takes a radically different approach. Superposition never collapses, ever. The wave function of the universe just keeps evolving according to the Schrödinger equation, smoothly and deterministically forever. The cat is both alive and dead, and when you open the box, the universe splits. In one branch of reality, you see a living cat. In another branch, another version of you sees a dead cat. Both exist, but in parallel quantum realities that can never interact or communicate with each other. Under this interpretation, every quantum measurement causes the universe to branch into multiple copies. There are countless parallel versions of you reading this right now, each experiencing slightly different outcomes of quantum events in their neurons. You're not collapsing wave functions, you're just experiencing one branch of an ever-splitting multiverse. The objective collapse theories propose that wave function collapse is a real physical process that happens automatically when quantum systems reach a certain size or complexity. Maybe gravity causes collapse. When enough mass accumulates, space-time curvature makes superposition unstable. Maybe there's a fundamental timescale where superposition naturally decays. And then there's the most provocative interpretation, the consciousness causes collapse hypothesis, which says that consciousness itself is the observer. Physical interactions don't collapse wave functions, only conscious observation does. Under this view, the cat's own consciousness would collapse its wave function, meaning it experiences being definitely alive or definitely dead even before you open the box. But this raises horrifying questions. What about bacteria? What about viruses? What about thermostats which respond to their environment? Where do you draw the line between conscious enough to collapse wave functions and not conscious enough to collapse wave functions? And if consciousness is required, what collapsed wave functions before conscious life evolved? Here's the truly dizzying part that should make you question everything. We've experimentally created superpositions with increasingly large objects. In 2019, scientists created quantum superpositions of molecules containing over 2,000 atoms, things big enough to see under a microscope. They showed interference patterns, just like electrons in the double-slit experiment. These molecules exist in superposition until measured. We're creeping closer and closer to the scale of everyday objects, and quantum weirdness is holding strong. The boundary between the quantum world and the classical world is blurrier than anyone expected. Your coffee cup might genuinely exist in a superposition of on the desk and off the desk for a brief instant until environmental decoherence or your observation collapses it so fast you'd never notice. But the principle remains. At the deepest level, reality is fuzzy, undefined, probabilistic until something observes it and forces it to choose. And we don't know why. You might be thinking, okay, this is fascinating in an abstract way, but I live in the macroscopic world, where coffee cups stay on desks, and cats are definitely either alive or dead. Why should I care about quantum weirdness? Here's why. This isn't abstract philosophy anymore. This is technology. This is medicine. This is the foundation of your present and the key to your future. Every piece of modern electronics, every computer chip, every LED light, every solar panel, every smartphone works because engineers understand and exploit quantum mechanics. The transistors in your phone are so small that electrons quantum tunnel through barriers that should be impenetrable. The device you're using right now would be impossible without quantum physics. And we're just getting started. Quantum computers are being built right now by companies like IBM, Google, and others. These aren't just faster versions of classical computers. They work on completely different principles. A classical computer bit is either 0 or 1. A quantum bit, a qubit, is 0 and 1 simultaneously, existing in superposition. When you run calculations on a quantum computer, you're harnessing superposition to explore vast numbers of solutions at once, like trying every path through a maze simultaneously. When you measure the qubits at the end, the wave function collapses to give you the answer. You're literally exploiting the observer paradox to solve problems that would take classical computers longer than the age of the universe. Google announced quantum supremacy in 2019, a calculation that would take the world's most powerful classical supercomputer 10,000 years, completed in 200 seconds by a quantum computer. We're at the very beginning of this revolution. Quantum cryptography uses the observer effect for theoretically unbreakable encryption. When you send information encoded in quantum states, any attempt by an eavesdropper to intercept it requires observation, which collapses the wave function and introduces detectable errors. You can't spy on a quantum communication channel without revealing yourself. Banks and governments are already deploying this technology. Quantum sensors exploit superposition and entanglement to measure magnetic fields, gravitational waves, and time with unprecedented precision. Quantum clocks are so accurate they lose less than a second over the age of the universe. These will revolutionize GPS, navigation, and our ability to detect everything from underground resources to dark matter. In medicine, we're learning that quantum effects might play crucial roles in biological processes. Photosynthesis, the process plants use to convert sunlight into energy, appears to use quantum superposition to find the most efficient energy transfer pathways. Birds might navigate using quantum entanglement in molecules in their eyes that respond to Earth's magnetic field. Your sense of smell might work through quantum tunneling of electrons in odorant molecules. Life itself might be exploiting quantum mechanics in ways we're only beginning to understand. And then there's the big question, the one that keeps physicists up at night. What does the observer paradox mean for consciousness? Some researchers, like Roger Penrose and Stuart Hameroff, have proposed that consciousness itself might be a quantum phenomenon, that your brain isn't just a classical computer made of neurons, but a quantum computer exploiting superposition in microtubules, tiny structures inside brain cells, to process information in fundamentally non-classical ways. If this is true, and it's highly controversial, then the act of conscious awareness isn't just observing quantum wave functions, it might be the collapse of quantum wave functions. Your thoughts wouldn't just observe reality, they'd create it, literally, at the quantum level inside your brain. We don't know if this is correct. The evidence is suggestive, but far from conclusive. But the mere fact that it's possible, that consciousness and quantum mechanics might be intimately connected, should make you pause and reconsider everything you think you know about the relationship between mind and matter. And if you really want your brain to melt, consider this. The entire universe started with the Big Bang, which was fundamentally a quantum event. Before the universe expanded and cooled, everything was in a dense, hot quantum state where the normal rules of space and time didn't apply. The universe itself began in superposition. So here's the ultimate question. Who or what collapsed the quantum wave function of the universe to make it definite? Before stars, before planets, before life, before any observers existed, the early universe was a quantum system in superposition. What made it choose to be this specific universe with these specific initial conditions, rather than the infinite other possible universes it could have been? Some physicists propose that the universe observes itself. That observation doesn't require consciousness, just quantum interactions, and the universe has been observing and collapsing itself through internal interactions since the beginning. Some, in a mind-bending twist, suggest that future observers reaching back through time collapse the past into existence. Under this interpretation, conscious life evolving billions of years after the Big Bang is what retroactively solidifies the history of the universe. The past doesn't exist as a definite sequence of events until future consciousness observes it, reaches back through the quantum fog, and crystallizes history. The universe needs its future to create its past. Still others embrace the many worlds interpretation. Every possibility became real. Every potential universe branched into existence at the Big Bang. Infinite parallel universes exist, each with different physical constants, different arrangements of matter, different histories. We happen to find ourselves in this one because this is the only one capable of producing observers like us. The observer paradox doesn't just change how we think about quantum particles. It forces us to reconsider the origin, nature, and fate of reality itself. So here you are, at the end of this journey, staring at these words on a screen. And now you know something that changes everything. Those words didn't have a definite configuration until photons from the screen entered your eyes. The electrons flowing through the circuits of your device to generate the image existed in quantum superposition, maybe here, maybe there, maybe nowhere in particular, until some chain of interactions and observations forced them into the precise arrangement you're perceiving right now. The screen you're looking at didn't fully exist in its definite state until you looked. You think you're passively watching reality unfold, like a spectator at a play or a viewer watching a movie, but you're not. You never were. That was the lie you were told, the comfortable fiction that made the universe seem stable and separate from you. The truth is far stranger and far more beautiful. You're an active participant in the universe's most intimate act. The the conversion of possibility into actuality, the transformation of the undefined into the defined, the crystallization of quantum fog into classical clarity. Every observation you make collapses infinity into one. Every measurement you take erases countless other potential universes where things went differently. Every moment you look at the world, you're choosing, whether you realize it or not, whether you intend to or not, which version of reality becomes real. Feynman was right to be humble about this. Nobody fully understands it, not really. We can calculate it with extraordinary precision. We can predict the outcomes of quantum experiments to 15 decimal places. We can use it to build technology that borders on magic. We can write equations that describe how wave functions evolve and collapse. But the why observation has this reality-creating power, why the universe seems to need a witness, why you're not just in reality but actively creating it moment by moment, that remains the deepest, most profound mystery in all of physics. 100 years after the birth of quantum mechanics, we still don't know what observation fundamentally is. We don't know if consciousness plays a role, or if it's just physical interaction. We don't know if wave functions really collapse, or if the universe constantly splits into parallel branches. We don't know if there's a hidden reality beneath the quantum fog, or if the fuzziness is all there is. What we do know, what experiments have proven beyond any doubt, is this: reality, at its deepest level, is not a collection of definite things with definite properties existing in definite places. It's a shimmering web of possibilities, a quantum superposition of all potential outcomes, all potential configurations, all potential histories, existing simultaneously in a state that has no classical equivalent. And observation, interaction, measurement, whatever you want to call it, is what selects one thread from that infinite tapestry and makes it the only thread that exists. So the next time you look up at the moon hanging in the night sky, remember, you're not just seeing it. In a very real, very quantum, very unsettling sense, you're summoning it into definite existence. The photons traveling from the moon to your eyes are collapsing from superposition into definite states. The moon itself, in principle, exists in a quantum superposition of all possible configurations until something, environmental decoherence, your observation, the universe observing itself, forces it to be definitely here, with a definite brightness, a definite phase, a definite position. The universe is watching you watch it. Reality is collapsing into form around you, because of you, through you. You're both the artist and the canvas, the observer and the observed, the question and the answer. Every particle in your body was forged in the heart of a dying star. Quantum fluctuations billions of years ago. Those particles exist in superposition until measured, until they interact, until they observe and are observed. You are quite literally the universe becoming aware of itself, collapsing its own wave function through the act of conscious observation. Consciousness might not be some mysterious ghost in the machine, separate from physical reality. It might be the mechanism by which reality becomes definite, the process by which possibility becomes actuality. You are how the universe decides what to be. Reality isn't something that happens to you, some external movie you're watching, some predetermined script you're following. It's something you do. Every moment, with every observation, with every measurement, with every interaction between your consciousness and the quantum field of possibility surrounding you, you're writing reality into existence. The observer paradox isn't just a weird quirk of subatomic particles. It's the fundamental nature of existence itself. And you, yes, you, reading these words right now, are standing at the center of it, collapsing infinite possibilities into the single, definite, miraculous reality you call your life. The universe doesn't exist out there, independent and separate. It exists in the space between observation and reality, in the eternal present moment where possibility crystallizes into actuality. And you are the observer. You always have been.